This is Dr. Brothers, and I'm going to be discussing lecture number 18 for ECE 3057. This is multi-threading and multiprocessing. So just a little bit of a recap from what we were talking about last time. We were looking at how you can have multiple processes. Each process will have unique code, data, and the pointer control block. There can be multiple processes on a single system, and each process can have multiple threads. So those multiple processes with multiple threads will enable us to do parallel operations if we have multiple processors. This will also enable a single processor to work more efficiently because you can have the consistent flow of information. So instead of just pausing the processor anytime or stalling the processor anytime you don't have the information you require, you can switch to a different thread and keep running while you wait for the system to go out and fetch the data, for instance, from the hard drive. So how do you use threads? It's kind of what I was just talking about. If you have some computation that's taking place, but then there's an I/O operation that interrupts it. Say that you're waiting for the data to be fetched from a hard drive. That takes a long time, so you stall during that period, and then you'll resume the thread where it requires the I/O data. However, consider if instead of doing that, you could have a single thread that is going through and doing the computations. There's a different thread that it might be able to jump to do the I/O operation while it continues doing processing until it gets to the point where it needs that I/O data, and then it can return it into here. So in a multi-threaded process, you can continue to work while you have a different thread go and execute the I/O operation. In a sequential process where you only have the single main thread, it does everything. So consider the system where you have a digitizer, a tracker, and an alarm. Each could run as its own thread, and data can be passed from the camera into the digitizer, into the tracker, into the alarm code. So if these are running multi-threaded multiprocessor, these can all run in parallel, and they can constantly work the data. Why would we want to do multi-threading? It is a better, more abstract, more modular way of solving a problem. So again, thinking about the system engineering process, how do you break something up into smaller problems that are easier to handle? This is one way. So you can separate the computation from the I/O processes. And in doing this, again, you can simplify these processes where you now have a processing thread and an I/O thread, and you can segment those into different domains. Take advantage of multiple processors and hardware support for multi-threading. This is the main reason we do threading. The main reason is to take advantage of multiprocessor systems, especially in the situation where we're doing GPUs, where there might be hundreds or thousands of processors that are available to us. The only way to utilize those multiple processors is to have something that can break it up, some structure to break up the code where the compiler and the operating system can understand what code will have to interact and what code is independent, so it can be distributed across multiple processors. In order to do that, one of the main things that I just said, they have to have the ability to understand, to communicate across. So all threads within the process have the same address space. So this means they have the same virtual and physical addresses. Communication is implicit by reading and writing to common locations. One other way to say this, you can think about these as having the ability to work on the same data set. That reduces down to the same virtual and physical address space. So if something is accessing a registered data element that resides in the virtual data space, all the processors that are running in this same process can all see that same data element. So we have to be very careful with that we know who's reading and writing to it at the same time. Hardware supports this shared memory. Even if threads are running on different CPUs, they can read and write to the same address via cache coherence. So as we're distributing these to multiple CPUs, we have a shared cache space that can be accessed by multiple CPUs at the same time. Well, they can read multiple. If there's a write, there has to be the controls to make sure that we don't invalidate the data. Synchronization. Coordination between the threads when updating the shared state. This is the most important thing to handle a multi-threaded environment. We have to maintain the data integrity. In order to maintain the data integrity, we have to make sure that all the threads that are operating on that same piece of data are not corrupting it. We'll look at how to do that today. So, POSIX Threads, Portable Operating System Interface. It's IEEE standard 1003. It started in 1988. This is threads operation, including the creation of threads, termination, synchronization, scheduling, data management, and process interaction. So all threads within a space share the same address space. That's what we were just talking about. So threads in the same process share the processing instructions, most of the data, the open file descriptors, signals and signal handlers, the current working directory, user and group ID. Each thread has a unique thread ID. This enables you to start and stop threads and to have ability to individually control them, change their priority. A lot of things can be handled through the thread ID. There's a set of registers and stack pointer that are each unique, because if you think back to the discussion that we had a long time ago about the CPU architecture, it's running these instructions. The instruction set that it's running is tied to that PC. So as soon as it needs to jump to a different section of the data, it needs to be able to reload its PC and reload its registers to a new state. So each thread has a unique set of registers and a unique stack pointer, so it can move independent of the other threads. There's a stack for local variables and return addresses. There's a signal mask, and then there's a priority. The thread priority will say who gets the processor cycle if there's multiple threads who are competing for that same processor. Race conditions. These are possible pitfalls. These are possible things that can now go wrong if you're doing multi-threaded. So we talked about this before at different levels. Each new level of hierarchy that we add into the architecture creates the possibility for new pitfalls. For instance, when we were talking about the CPU architecture and we just had single cycle operation, that meant that one command was going to be processed through the fetch, decode, execute, memory, and write back stage. So the time it took to get through that entire process was one clock cycle. However, we went to the multi-cycle, and then we went to the pipeline. The pipeline now had the possibility that the fetch would interfere with the execute. It might have a variable that is being reset in the prior operation that's not ready for the next. So now we have that same situation, except we've moved up some degrees in the hierarchy. So now we have the possibility that two threads could be reading and writing the same variable. So this is the same type of situation that we've been talking about on a lot of these advanced architectures where we add more pieces of hardware that are sharing time. That creates a situation where we can read and write the same variables. And so if we have a race condition, we don't know what the value is going to be or if it will be correct. We also have thread-safe coding. All the functions must use thread-safe variables. So we don't want to use globals or static variables. We want to have these thread-safe variables so that we can control who's manipulating them. And so if it's a global variable, you know, things outside of this function call might have access to it, and we want to restrict it to only the inside the box with regard to the threads that we're seeing. Mutex deadlock. So this happens when a thread is not unlocked. For example, when two threads are waiting for each other, you might have a thread pause and wait for data from another thread. But if there's somehow like a circular definition that's going on between those two threads and they end up waiting for each other, they might both break. You might break your whole system because one variable is going to be waiting for the other variable, or one thread will be waiting for a variable, and the other thread is waiting for the other variable, and those variables are set within the threads that are currently locked. So let's look at a little bit of an example of how this all could work. We're going to go back a couple of, this is thinking back a couple of slides about that example where there was the webcam that was feeding into a couple of blocks. One of them was called the digitizer block, and the next one was called the tracker, and then the final was called the analyze. So if we look at this, what it's doing is it's taking this digital image, and if there's room available in the buffer, or if the buffer has space available in it, if the buffer available is greater than 0, then what we're going to do is grab the digital image, then we're going to push it onto a frame buffer. We're going to move the tail of the frame buffer, and then we're going to decimate the buffer available. So if the buffer available has something in it, we're going to grab that buffer and put it into this frame buffer variable. The tracker, it will look at this buffer available and see if it's less than the maximum value, and if it is, it's going to take from the head of the frame buffer, and then it's going to increment the buffer available, and then it's going to send that track to the analyze circuit. So here's one of the big problems that could happen with this. If the buffer available is equal to the buffer available plus 1, and that's set in register 1, and then we have register 1 is incremented, and then that register 1 is returned back to the buffer available. But now let's say that you have this other thread that's running, and these are running simultaneously. The buffer available is going to be decremented by 1. But it's going to use register 2 of the space, and the buffer available is going to be put into register 2, and the register 2 is decremented by 1, and then that's stored back into the variable. So while these opcodes are being executed, there's the possibility that we'll have a situation like this at the bottom. So the register is stored off, the register is incremented, but it hasn't saved back yet. Then register 2 grabs the buffer available and starts to decrement it. Register 1 is stored back into the buffer available, and then register 2 is stored back into buffer available. So you can see what has happened here. The buffer available should have been set to a 5 at the end. We started off with a 5, and we're increasing by 1 and we're decreasing by 1, so it should have went up to 6, and then it should have went back to 5. But what happened, because these two were operating on the same piece of data simultaneously, they actually had a race condition, and in this particular instance, register 2 won the race. However, threading processors are not deterministic processes, so these might have hit a miss condition in the cache, and they might have happened in a different order. So we can't say that this is always going to be the way it's going to go. We can't say that register 2 will always write to buffer available and that register 2 will be pulled before register 1 will write to buffer available. We don't know. So this is why we need to put the communication layer between the different threads to make sure that we're not corrupting our data. So here is an example of a C++ application. The C++ application is going to create a couple of threads, one thread for the digitizer, thread 1, one thread for the tracker, That's thread 2. These threads are pthread objects. We have a couple of variables. Buff available is going to be set to the max size to start off with. The max size is designed as a static max 8. Image type frame buff is of the max size. Then we have this blocking pthread object so that we can buff lock. If somebody is playing with the buffer, we will set the buffer lock, and it will prevent multiple threads from creating the problem that we saw on the last slide, where they were both trying to modify the buff available variable at the same time. Once the threads have been run, we have these pthread join at the very end. What these do, these wait until both the threads have exited before this entire process can exit, because we don't want to just have it run straight through before the threads have had a chance to actually complete the operation. And the answer is, shoot. Do these lines need to be mutually excluded? The ones that are important to be mutually excluded are the ones where there's the same variables being written. So the analyze does not matter. The track image read, that does not matter. We need to make sure that we're locking. This is a race condition. Let me get back there. This is a situation where both threads could lock out each other because it could sit in the do nothing state on both of them. Alright, or it could get locked in the do nothing state. So this is a much better solution. It does not actually lock out on the read. There's no reason to lock out on the read. Is it functionally correct? Performance? The waiting wastes processor cycles and energy. So even though we're saying do nothing, all the processor is now doing is looping, and it's doing a branch if equal, branch if equal, branch if equal, and it's just continuously checking. So even though we're not doing anything, the processor is still burdened with do nothing states. So here's how we can fix that. Instead of burdening the processor with doing nothing, what we can do is say we're going to use conditional variables. What this does, there are two threads that are running, and there's data being generated in one thread that's needed in the other thread. So we can set this thread pthread conditional wait, and then pthread conditional signal. So this will signal to the waiting threads when the data value C is ready. This is done by using a couple of different signals. Pthread conditional wait blocks for a given signal. Pthread conditional signal one waiting thread. So this is how a pthread conditional signal. Thread 2 is telling thread 1 that the variable is ready and that it can go ahead. Pthread conditional broadcast signals all waiting threads that some variable is ready. Here is an example of using this type of application. We're again going to go ahead and lock, but now this pthread wait is going to be applied to that locked thread. So it's going to sit there and the thread is locked and waiting. So once it receives the unlock or the pthread broadcast, in this case we're doing a broadcast, when this pthread broadcast is sent out, it will get this buff not empty, and it'll catch it on this side, and it will unlock and it will move forward. Same thing happens here. If the buffer is available, or buff not full will be set, and that buff not full will be sent to this side, and it will go on through. If this conditional check, if buff available is equal to max, is the only time it's going to go in to this conditional wait. If the buffer is not full, this will continue straight through and execute the remainder of the code that is unchanged. Is this functionally correct? Yes. How about the performance on this one? It does concern concurrent operations, and there is no busy waiting. So instead of now sitting in that infinite loop while it's waiting, it's just going to do a thread conditional wait. In order to do these conditional waits, we need to add pthread conditional variables. And we have the not full and not empty conditional variables added to the main code. So a summary of the thread function calls. We have a pthread create, and this does exactly what it sounds like. It creates the thread. Pthread terminate, it kills it off. The lock, this will lock a thread that is currently in use by some other threads. Calling thread blocks if the thread is currently used by some other thread. Then try lock, it's going to try to get a lock on it, or it returns a failure if the lock is currently in use by some other thread. So if two threads are both trying to lock on the same thing, this will try, and if it tries and fails, it will let you know. Pthread unlock, it releases the variable for others to use. Pthread join, as I showed in that main example, there were multiple threads that were running, and you wait for them all to conclude before you allow the program to move on. Pthread conditional wait, calling thread blocks on the conditional variable. For example, the buff not empty, and it releases the buff lock. If lock is not currently held by the calling thread, it errors out. Sorry about this. It throws an error if the lock is not currently held by the calling thread. And then pthread conditional signal, a thread working on a conditional variable is woken up. Awakened thread either is ready for execution if lock associated with it is currently available. If not, thread is moved from the queue for a conditional variable to the appropriate lock queue. So once it's woken up, it is said, okay, you can now have access to this variable. If it's already in a locked state, it will take that variable and manipulate it and continue working on it. If it is not in a locked state, it gets put into the queue to receive the lock on the variable. So the variable lock is what allows one thread to operate on one variable at a time. So we want to avoid the multiple threads writing to a single variable. So how does this work? How does it actually get implemented on the OS level? We have kernel processes and user processes. So as this top side, which is visible to the user, we have a kernel side process which controls the PC, and that is visible to the operating system and the hardware. So imagine that we have multiple CPUs. Each CPU is going to be assigned to do something. So this could be one two-way multi-threaded CPU. And so this might be a physical single CPU, but it might have multiple cores. And so the operating system will determine how to schedule these different things. And this is going to be the topic of lab number 4. So hardware support for multi-threading. Implement a lock, atomic operations, and check for correctness. Thread level parallelism support. This is done for performance. So why do we care about mutual exclusion? So why do we care if these two different threads are going to try to write the same data at the same time? So assume again both threads are trying to execute some chunk of code that's going to both try to go to this data piece. Both threads might read R5 is equal to 0, update it to 1, and then write 1 in some order. However, the correct value of data should be 2 if they're both executing the same chunk of code. This one should increment it, and then this one should increment it. Solution: locks. So a test and set lock, if we have a lock pointer and then a data pointer, and then on the other thread we have the same thing. So both threads now execute this critical section of code. They copy the value at the lock pointer to a register lock test and update the value of memory lock pointer to 1 automatically. So this is how it looks when we add in the lock test. So branch if not equal, acquire the lock. So this is the hardware layer of implementing the controls that we were talking about earlier, where both threads are trying to access the same data. At the end, we're going to release the lock and put it back in. So we have this lock location, which kind of holds the key to the data, and only one person can get the key. One CPU can get the key at a time. So test and set implementation. CPU A issues a test and set instruction. The original value is read out and sent to the CPU A and stored in the lock test, and at the same time updated to a 1. If the original value was 1, the lock was in use and CPU A will retry. If the original value was 0, the lock was not in use and CPU A can proceed to the critical section of the code. So in this way of reading and writing to that kind of a test variable, we can see if it has to wait for the actual data. CPU 2 issues and tests and set instructions. The one that reaches the memory first wins. Caches naturally complicate this further. Implementing locks with caches is beyond the scope of this class. So, atomic read, modify, write instructions. So example, test set lock in the previous slide. So this is a read, modify, write. So it is doing all those operations in this one opcode command. It's getting the data value, modifying the data, and writing it back. Others, compare and swap, load, linked, stored, conditional. Atomic operation, no other interleaving of any memory access between the read and the write. So the majority of the processes that we're going to do in CPU operation, you would get a couple of registers and you would grab one and then grab the other register, do some type of mathematical operation on that, and when you have completed that mathematical operation, you would store it back into the output. So we need to ensure no other core inserts its LD store instruction between the lock read and the write. So we need to implement a lock. We need to make sure that we have that locked down for that atomic operations for correctness. But in order to go beyond just the implementation of securing data, we need to have thread level parallelism support. This is done for performance. So looking at the lock, that was done to make sure that we have correct data read and write. The next thing we're going to do is talk about how do we actually implement multiple threads in hardware architecture in order to support this improved performance. Here's an example of how we do that. We will start this off by having multiple PC counters that are going to go through a mux, and they're going to go through the instruction register, and then each one of these is going to have its own register bank. So the general purpose registers are going to be coordinated with each of the possible threads in this CPU core, and then the rest of this architectural level looks the same the same as we normally have. So in this way, we can change between these multiple threads as the data is availability and make maximum use of that piece of hardware. So how do we carry the thread select down pipeline to ensure correct state bits are read and written at each pipeline stage? Each thread in the hardware appears to the OS as a CPU. So this is a multi-core style implementation. So given each of these multiple PCs, these are multiple things that the operating system can assign to these resources. So even though they're making use of the majority of this hardware, it is unique from the eyes of the operating system. So if we have multiple processors, we have multiple threads, we have multiple processes. This is what it looks like as we actually start to put these on silicon. We have a bunch of different processing cores. These are the CPU architecture. Then we have a large bank of shared L3 cache. Each one of these cores will have its L1 and L2 cache, but there's a big bank of shared cache. The memory controller on the top, and the queues and the I/O on the bottom, taking data in and out. So there are some unique challenges with multiple processors that we don't see in a single processor system. How do we scale it up? As we saw in the last slide, we have the shared L3 cache. That has now become one of the main areas of the core of this chip. So the space consumed by the L3 cache, which has to have connections to all the processor cores, the shared cache is now becoming a major part of this chip. So how do we share that as we get more and more and more? Because the interconnections are going to build up to be very, very, very dominating on this chip. How do you get communication? How do you make sure that everything that's happening is parallel? So there are overheads associated with the distribution of data. And when do you get to the point where you cannot overcome the overhead anymore in order to make a simple task parallel? So there is a diminishing return on a set size of an application in order to create parallelism. Programming coherence, you have to have something that it will be able to be distributed out, and scheduling. So let's look at workload. Say that we have sum of 10 scalars and a 10 by 10 matrix sum. So what's the speed up from 10 to 100 processors? For a single processor, the time is going to be 10 plus 100 times the time to add. So 10 scalars, 10 by 10 matrix, this is where the 100 comes from, and the 10 scalar values are going to be multiplied or summed with the 10 by 10 matrix at the cost of one addition each. However, if you have 10 processors, now you can do 10 times the operations at a single time, plus 100 divided by 10, because this is a 10 by 10, but we're going to distribute it out to these 10 different processors, times the time of a TAD is equal to 20 times TAD. So we are going to quite a significant, we went from 110 times TAD to 20 times TAD. So the speed up total is going to be 55% of the potential operations. 100 processors. Time, again, we have 10 scalars, 10 adds, plus this 10 by 10 matrix, which we're going to split up amongst the 100 processors now. And each one of those is going to have the addition operation. So that's going to be equal to 11 times T add. So the speed up is going to be 110 divided by 11, which is going to be equal to 10% of the potential, compared to 55% of the potential here. So as we're going from 10 processors to 100 processors, we see these diminishing returns start to appear. Idealized model. Assume load can be balanced across all the processors. So ideally, we have this perfect setup where you can just take it and just perfectly distribute it amongst everything, and you will get a divide by n style speed up. But that's not how it works in the real world, because in the real world, the mathematical operations oftentimes are interleaved with the other operations, so there's some degree of connectivity between them, and you can't just perfectly split it up. So what if we have a matrix that is size 100 by 100, and we want to do a single processor? So again, we're going to have the 10 times 100 times 100, all at the cost of T add. So for 10 processors, we do the same arithmetic, and we get 99%. 100 processors, speed up is going to be 91%. So dramatic change from a single processor to 10 processors, 10 processors to 100 processors, not as much. Idealized model, assuming load balance. So strong scaling, problem size is fixed, as in this example. Weak scaling, problem size is proportional to the number of processors. So 10 processors, 10 by 10 matrix, time is equal to 20 times T add. 100 processors, 32 by 32 matrix, we get this time is going to be equal to 20 times add. So the time is going to remain constant, but we're going to scale up, say, the image size that we could process in order to meet the same size. And this is one of the things that they do, like with high definition TV. We talked about the football example earlier, where they're putting the first down line across the field. They can increase the resolutions of their cameras and increase the resolution of the image processing only up to the maximum that they can transmit. So they don't really care what's the maximum speed they can go. They care what's the maximum data that they can go at a given speed. Does that make sense? All right. So consistent performance in this example. So this one, we're not really worried about how much an increase we get in the system, but how much data can we increase at the same time. So this is for a fixed size system. We grow the number of processors to improve the performance. Performance of multiprocessors. Do n processors mean a speed of n? Speed up is going to be equal to the runtime of the original divided by the runtime of the new. If we have runtime is going to be in the instructions times the CPI times the clock period. Ideally, all instructions can be equally divided across n machines. Each machine runs instruction underscore total divided by n. But is this real world at all? We've already seen so many times that the instructions are interleaved with each other, meaning that they depend on the result of the previous instruction to get to the next instruction. There's data conflicts, there's all sorts of things that we need to take into consideration, so this is very hard to achieve. In this instance, though, in the ideal situation, we have CPI and clock period is the same across all machines, so it's perfect. Everything is perfectly aligned. In the ideal situation, the ideal speed up is n. So obviously, do you think this is feasible? No. Why not? One of the main reasons is the communication across the systems. If an opcode depends upon the instruction prior to it, the data from the instruction prior to it, the same is true for threads. We have multiple threads. One thread depends on the data result from another thread. So as you put these threads together, there become a lot of interdependencies. In the example that we went over before, in the code example, we had a data buffer where these two processes were working on the data. One was putting it into the buffer, the other was taking it out of the buffer. So there was this choke point of the data buffer where we might have been able to run faster, but we had to put that data into the buffer to communicate it to the other thread. This limits the CPI. Parallelism limits the number of instructions that can run in parallel. Okay, so suppose that we have a CPI of 0.4, assuming all references hit in the cache. So we have a remote request rate of 0.002, we have a remote request cost of 400 nanoseconds, and we have a clock rate of 3 gigahertz, clock period of 33 nanoseconds. So if we take all this, put it together, the new CPI, given this multiple processor situation where they're going to have to do these remote data requests from another machine, we can take the original, which was 0.4, we can take the remote rate, the rate of having these remote requests, multiply that by the time of the remote requests, normalized by the clock rate, and we can see that the output is going to be a dramatic slowdown. We're going to go from a CPI of 0.4, request rate is 0.002, but the request cost is 400 nanoseconds. So it's a very, not even that large a time, but it takes a number of clocks. Speed up is n divided by 7. So in order to even break even on this overhead, on the overhead of creating a parallel process, we're going to need 7 processors just to be able to break even, because we have to now distribute the data amongst multiple processors. Speed up, 1 divided by 1 minus f plus f divided by n. F is the fraction of the code that is parallel. Ideally, everything can be parallel, but that's not going to be true. It's not going to be true. We have to do things in serial in order to get to the parts that can be parallel. So we have to normalize the speed up given the percentage of the code that is parallel and the number of processors. So suppose that the fraction of the code that is parallel is 0.9, so 90% we can make parallel. The number of processors is equal to 100,000. Speed up is equal to 10. This is limited by the serial portion. So even though we have this massive number of processors, that 10% of the code that requires serial operation is still going to dramatically slow down the overall effect of the parallelization of the code. Programming multiple processors, we need shared memory and we need message passing. In order to have these systems work, we need to have shared memory between the processors that everybody can access and see the same data. All threads on all processors see the same address space. So this means that if you have threads that are executing the same task, they all need to be able to see that same memory space. Implicit communication by reading and writing to memory. So we are not explicitly saying, okay, I'm going to have thread number 2 start thread number 3, but thread number 2 might lock a variable, and then he might unlock a variable, or he might actually say, hey, this data is ready. So they're not explicitly communicating, but they're using the data to implicitly communicate to each other. If processor X writes to address A and processor Y will eventually see the value of address A. So we're not telling the two processors that the data is there, but the threads that are reading that data will eventually see it. So caches complicate this scenario. Everything that we've talked about in the previous couple of lectures about how we have these cache systems, they must be very fast. We must have multiple ways in order to present the data to the processor. This makes it very hard now because we have multiple processors that are updating multiple pieces of data. And then we have these threads, which are now straddling between the operating system and the hardware, that again, they're going to update these caches. So it gets very complex, and we have to pay very close attention to locking the data, and we also have to pay attention to the register read writes, that we find out that data that needs refreshed and get it refreshed through all the level 1, level 2 caches. Each processor has its own address space, explicit communication via send and receive. So now we're going up one level in the hierarchy, basically. So each processor has its own address space, and it can send and receive messages. The programming model, the process plus the interprocess communication, the MPI. MPI can run on shared memory machines as well. So using this process, we have caches that can implicitly communicate, and we have processors that can explicitly communicate. Scheduling on multiprocessors. Simple policies. Lab 4 assignment, we're going to do FIFO, first in, first out, round robin, so everybody goes around the circle and everybody gets turn. Shortest remaining time first. Whoever has something that is going to be done real quick, they're going to get the access first. Complex policies, locality, place threads close to their data. We haven't even started to talk about the actual physical locality, but as you start to get bigger and bigger and bigger systems, especially systems that are distributed across multiple data, across a data center, for instance, where the physical data might be stored in one place and the CPUs might be in another, how do we start to allocate resources to put them at their highest probability of getting the data in the least amount of time? Quality of service, cache affinity, all these things are making sure that the data is ready when it needs to be.